Hello everyone, welcome back to this week's algebraic graph theory seminar. This week, Nathan is going to tell us about the derangements.
Great, thanks for the introduction. So I was hoping this would be out on the archive before I gave the talk, but no such luck. So all this stuff, I hope to get it out soon, but you'll be getting some breaking news. Okay. So I think we all know what a derangement is, but let's just be clear that we know what that is. So it's a permutation with no fixed points. Okay. And the derangements is a union of conjugacy classes of the symmetric group. So the C sub lambda, this is the conjugacy class corresponding to the cycle type lambda. And this notation here, FP of lambda, we're just counting the number of fixed points of lambda, i.e. just the number of parts of size 1. Okay, so there's lots of well-known expressions for the derangements. This first one you've probably seen in a first combinatorics class, just the principle of inclusion-exclusion. From this, you can derive a pretty slick asymptotic formula that holds, or I should say an estimate that holds for sufficiently large n, namely n greater than 1. And then we have some other interesting recurrence relations here. Okay. So the derangement graph is a Cayley graph, a normal Cayley graph. So it's a union of conjugacy classes defined on the symmetric group. And there's another way of looking at this. You can think about, you can throw away groups and think about perfect matchings of the complete bipartite graph, K and N. And you have two matchings that are joined by an edge if their matchings share no edges. Okay, so this graph is the reason why people were interested in this graph was because the independent sets are interesting. So in particular, there are these so-called intersecting families of Sn. And this connects to Erdős-Corrado, and so that's an interesting topic for another talk that I've probably given in this seminar already. So that's the main reason why this derangement graph has been considered. Think of it as like an analog of the Kneser graph, which is another mainstay of algebraic graph theory. So I'll get right to it. So the eigenvalues, so here's an expression for the eigenvalues of the derangement graph. Okay, so they're just, you can think of these things as just character sums. So we have, so this chi x, chi lambda, this is the irreducible character corresponding to lambda, evaluated at the conjugacy class mu. So characters are constant on conjugacy classes. So that's how we get that second inequality. So it's just a scaled character sum. That's all it is. And you know, that sounds simple, but like what on earth does that actually, I mean, what's a nice formula for that? So, you know, it's not clear at all. So in particular, there's an exercise in Stanley's exercise, what is that, 7.63 of Stanley's second volume of enumerative combinatorics, where he's able to tease out a nice formula when lambda is a hook. So it's when it's a hook shape. So we have one part of size k and the remaining parts are of size 1. So he's able to get a nice combinatorial formula there, but it's open what the other, what a nice combinatorial formula is for these other shapes. And so that's something that we're going to talk about in the remainder of this talk. Okay, so the derangement graph, I'll run out of time if I go through the list of all the, papers that feature the derangement graph and its eigenvalues. So I'll just flash this list up here. Maybe we can come back to it in a post-talk discussion of it, but lots of people have studied this graph and have been curious about its eigenvalues and like what a nice expression for it is and so forth. So, okay, so the derangement graph has a cousin, and we call it the perfect matching derangement graph. And so you can define perfect matching derangements in sort of the same way as you can derangements. So so here we're going to call we're going to say that M and M prime are derangements of one another if they share no edges. So if I take the union of M and M prime, where those are perfect matchings of K2N, and that union, if they have no edges in common, then we join them by an edge. Okay, again, people were interested in this graph because of the independent sets. They're these intersecting families of the perfect matchings. This is this is one of my first serious papers in math, I guess. I don't know. So I studied this in my master's thesis, and so yeah, it's an interesting graph. So its eigenvalues are even more complicated, I would say, because you know, this will take us. You know, if you've seen some representation theory, maybe you know what some of these words mean, like zonal spherical functions, Gelfand pairs, and whatnot. But basically, these zonal spherical functions, these are sums of characters even. So it's like, so as if the first expression wasn't complicated enough for the eigenvalue eta lambda 1, these eta lambda 2s, they're even more complicated. So hence 3 question marks versus 2 question marks in the previous slide. So so anyways, yeah, so you know, what on earth is a nice formula for these. So hopefully that's something that is something that we'll cover by the end of this talk. We'll certainly have time for that. Okay, so yeah, I mentioned that this was one of the first things that I started studying, and some other folks have jumped on board and also looked at this graph as well. It's very interesting. It has a lot of algebraic properties that are very similar to the permutation derangement graph. So yeah, maybe we'll pause here. Do we have any questions about these 2 graphs that are kind of going to be the centerpiece of the remainder of the talk? Okay, so if we have no questions, we'll keep going. Right, so we mentioned that these the eigenvalues, these eta lambda 1 and eta lambda 2, the eigenvalues of these graphs, we said that, you know, that they have some similar properties. So like in particular, this perfect matching derangement graph kind of parallels what happens for the permutation derangement graph in a sort of interesting way. So this, so the way to talk about both of these, the eigenvalues of these graphs simultaneously, are these Jack polynomials. And so if you've seen these before, let this slide be a refresher. If you haven't, it's no big deal. We're not going to be really doing much manipulations with Jack polynomials. But suffice it to say that the eigenvalues of the permutation and perfect matching derangement graphs, they are, we can write those eigenvalues in terms of these so-called Jack characters, which we'll see on the next slide. And so these Jack characters, we're taking the Jack polynomials, in particular J lambda, and we're writing them in the power sum basis, and the coefficients that we get, we call these the Jack characters. Okay, and so in particular, we have the following. So we have this lambda Jack derangement sum. So if you plug in alpha equals 1 and alpha equals 2, you get the perfect matching, or you get the eigenvalues of the permutation and perfect matching derangement graphs respectively. But for other values of alpha, they don't, as far as I know, they don't correspond to any eigenvalues of graphs that I'm aware of. And in particular, you know, alpha can be any real number. So, and it's, you know, we have uncountably many lambda Jack derangement sums based on, you know, your choice of alpha. So I'll put 4 question marks here because, you know, it seems like we're only making this problem harder. But I promise you we're not. In fact, Jack derangements, like these Jack polynomials, are the proper way of looking at it, rather than trying to do some representation theory to understand what eta lambda 1 and eta lambda 2 are. So, right. And so I put derangements in quotes here because like the previous, or like the next line says, we don't really know of any combinatorial models besides alpha equals 1 and alpha equals 2. So alpha equals 1 is the permutation case, alpha equals 2 is the perfect matching case. Okay, so but nevertheless, we can get what I'll call an opaque expression for these Jack derangement sums via shifted Jack polynomials. And so we'll talk about what shifted Jack polynomials are. well, I guess we won't really talk about, we won't define them actually, because we're going to quickly dispense of them, because turns out that we can, we won't have to define them. We can just use some combinatorics that we'll see on the next slide to where, you know, to where we can skirt the issue. And really, you know, if I were to actually define the shifted Jack polynomials, it would take a bit of time. So it'll be good for all of us. Okay, so this theorem is essentially due to a recent result of Paul Rinteln. So he proved this result actually for zonal spherical functions. If you know what those are, that's essentially just the case where alpha equals 2. But, you know, mutatis mutandis, you can get a proof for not the shifted zonal polynomials, but the shifted Jack polynomials. Okay, so here's the result. And so we'll get a nice combinatorial expression for this JK star lambda alpha. Okay, so when I plug in this alpha here to this shifted Jack polynomial, I'm specializing that I'm x1 to be lambda 1, x2 to be lambda 2, ... So that's what this means here. Okay. All right, so we get this alternating sum of shifted Jack polynomials that I promise you will have a nice combinatorial meaning. So just be patient. So let's talk about, so to get this combinatorial meaning, we'll use some terminology that Yuval Filmus and I came up with earlier this year. So they're called Tableau transversals. So we have, we're going to say a K transversal T of a Tableau lambda. So I'm thinking of lambda as like a Ferris diagram right now, is just a set of K cells which forms a partial transversal of the columns of lambda. So let's see two examples. So I have a shape 4, 3, 2. So the cells that are in orange, that forms a 4 transversal of this shape. So to disregard the numbers that are in these cells for now. So if I just look at the orange cells, that's a 4 transversal. If I look at the green cells, that's a 2 transversal. Okay, so the numbers inside these cells that I have, these are the alpha weight of this transversal. And so we define this alpha weight to be as follows. So I take a cell. So let's take this cell here, alpha plus 1 in row 1, column 2. So I look at the number of cells to the right of me in this row. I see 1 there. And so I have an alpha, and then I add 1. So right, so the alpha weight of the of this orange transversal is alpha plus 1 squared, and then the alpha weight of the 2 transversal is just 1. Okay, so let's let T sub lambda K be the collection of K transversals of lambda. So the set of all such K transversals for a particular value of K. Okay, so here's the combinatorial expression for these shifted Jack polynomials that I promised. And so it's not due to me. It was discovered much earlier by Alexanderson and Ferret. In particular, they showed, so this also came up in some work with that I was doing with Yuval in another area. We were looking at harmonic analysis on the space of perfect matchings. In particular, we were looking at some differential operators acting on the space of perfect matchings, and these this sort of combinatorics popped up, and so we did some digging around. It turns out that it popped up earlier in Alexanderson and Ferret's work. So they were the first to notice this expression here. And so if we plug in Rinteln's result plus Alexanderson and Ferret's result and do a little bit of reindexing, we have the following. So we have this expression for our Jack derangement sum. So I have this, so it's starting to look nice. So we have this sign out here, and then we have this alternating sum here, but we still have no idea what is going on here, because we're taking these transversals and we're summing over these the alpha weights of each of these transversals. So this looks like a very sort of complicated combinatorial sum. Okay, so we're going to want to boil this down a bit. And so to boil this down a bit, it helps to reformulate these Tableau transversals in terms of something that's a bit more familiar and is also related to more to the character theory of SN. And so it's these so-called colored permutations. And so if you've been keeping your eye out on like recent results in the character theory of SN, you might have noticed that there's some nice formulas for the character theory of SN that involves colored permutations. Some of them are due to Fourier. And the colored permutations, like these Tableau transversals, we can think of them as colored permutations in the following way. So, okay, so for each I in my symbol set N, I'm going to define a list of colors. So 1 through MI for each I. Okay, so a colored permutation is just an assignment of colors, C1 through Cn, such that the color that I assign to symbol J is a valid color. It's in my list of colors for J. And also sigma is and so we're also requiring that sigma be a permutation of the N elements that has the following properties. So if I maps to J, then I and J have the same colors. And so what this, what this implies is that each cycle of sigma is monochromatic. So I know that's a lot of words, so let's give some examples to be sure we understand what's going on. So we'll give an example here. So if I take a partition lambda, so any such lambda defines a color list on a symbol set where the symbol set, we take it to be the first row, and our color list is going to be the transpose, and we're going to look at the ith part of that transpose for the color list. So let's see an example. So we have so maybe we have 1, 2, 3, 4 along the first row, and green is color 1, yellow is color 2, and red is color 3. So I have that 3 maps to itself, and it gets the first color, and then I have that we have a 3 cycle here that is where all of them have the color yellow. Here I have a 1 cycle where 1 is red, a 1 cycle where 2 is red, and we have a transposition here between 3 and 4. And here we just have all the symbols are colored the same color, so they're all colored 1, and this is just a 4 cycle. Okay, so there's this, so we get this this correspondence between these things that we were calling Tableau transversals and colored permutations. Okay, because so for instance, let's look at this one here. So if this was my transversal, if I took the first cell in each of these columns and I considered its alpha weight there with alpha equal to 1, it would be so that would be 4 factorial. And so if we consider all ways of if we consider all permutations, so rather than just this particular one, then we get the right alpha weight. Okay. So we're going to let S sub lambda be the set of all. So for a given lambda, we're going to let S sub lambda be the set of all such colored permutations. Okay. So this is just formally we write this out as follows. Okay, so maybe I think in the interest of time, I'm going to skip the perfect matchings, but you can sort of do the same thing with perfect matchings and not much changes. Okay, so let's go to the colored derangements. So we take a colored permutation, C sigma, and we say that's a derangement if, when I look at sigma, if I maps to itself, then it better have a color other than 1, or in this, so what we've been calling green. So it needs to be, it can't stay in the same place. So for instance, if we looked over here at the first colored permutation that we saw, this would not be a derangement because I had the symbol set 1, 2, 3, 4. And then we saw that 1 gets mapped to 4, 2 gets mapped to 1, and 4 gets mapped to 2, and 3 gets mapped to itself, but it stays on the first row, so it doesn't get a new color. So that's not a colored derangement. However, the second one we saw, it is a derangement, because even though 1 gets mapped to 1 and 2 gets mapped to 2, they get different colors. So it's not color 1. And of course, this permutation 4, 3, 2, 1, this is just a permutation in the traditional sense. So we assign them all the same color, and so it's a derangement in the traditional sense. So right, so this is a 4 cycle. Okay, so these color derangements are going to be important for the main result. So I'll say a little bit more about them here. So let's let D lambda be the set of derangements of S lambda. And let's refine this further and say that D lambda sub K is going to be the set of derangements that have exactly K disjoint cycles. Okay, so of course, it's clear that we can write the number of such derangements as the sum of these derangements with exactly K cycles by just summing over all possible lengths of K. And so it turns out that for lambda, when we substitute lambda equal to the trivial partition n, we actually recover these things called the associated Stirling numbers of the first kind. And I had no idea that people had even studied these things. So this is the number of derangements of Sn that have precisely K disjoint cycles. And so if you want to read more about that, you can go to ComTet's Advanced Combinatorics textbook. So this is ancient text on combinatorics, where I think these are defined in an exercise. Okay, so yeah, any questions so far on these colored derangements? So it's pretty much the same as Sn, only now we're adding colors. And you know, if you have a fixed point but a different color, then that saves you. Otherwise, if you don't, then you're not a derangement. Okay, so here's the main result. So we're going to define these Jack derangement numbers to be it's going to be a polynomial in these dk lambdas that we described on the previous slide. So these are the number of derangements of S lambda that have precisely K disjoint cycles. So we're going to call this when we plug in alpha, we get a number, and we're going to call that the Jack derangement number. So the main result is that the Jack derangement sums, which were these eta lambda alphas that we defined, was the sum of the Jack characters. So those, in fact, equal the Jack derangement numbers that we've just defined on this slide, up the sign. So that's what the main result here states. Okay, and so just a quick note that if, so these dk lambdas, these are counting size of a set. So clearly they're non-negative. And so when we plug in alpha, like some non-negative alpha, we're going to get something, of course, we're going to get something that is non-negative. And this is important because if you know a thing or two about the permutation and perfect matching derangement graphs, there's this thing called the alternating sign theorem, which is a theorem that says that the sign of an eigenvalue is determined by the number of parts below the first row, or the number of cells below the first row. And that's what this coefficient here means. And so like this main result immediately applies like a generalization of the alternating sign theorem. Instead of alpha equals 1 and alpha equals 2, we now have, you know, for all non-negative alpha. Okay, so it turns out that this is actually, as I was going through some of these proofs again, I don't know why it didn't dawn on me earlier, but it's this is actually somewhat easy to prove for alpha equal to 1 and also 2, but we're just going to talk about 1. Okay, so for alpha equal to 1, our main result, we're just plugging in alpha equals 1. And so the way we're going to prove this is through it's just a inclusion exclusion. That's essentially the same. It's the same proof for like the derangements of Sn. And in fact, if you plug in lambda equal to the trivial partition, just one part in, and alpha equals 1, then you actually recover that proof. And so we'll let's walk through this proof. So okay, so first, recall we had this expression when we combined Rintel's result with Alexanderson and Ferre's result. So we had this complicated expression. Right? We still don't know really what's going on here, but through this correspondence that we just talked about between these Tableau transversals and these colored permutations, this sum here, we can replace this sum with this sum here, and note that mu is going over all the ways that I can remove k columns from lambda. So I take all shapes that I can obtain by removing k columns of lambda. So let's think about this a little bit more. So that this t lambda lambda 1 minus k, remember that these are all the Tableau transversals that we can get by selecting lambda 1 minus k columns and picking a cell in those columns. So if we go over all ways of removing k columns and we take all Tableau transversals that we get in that manner, then we get that explains this correspondence, right? So so now these colored permutations now are counting the number, they're counting the alpha weights now for all these possible Tableau transversals. Okay, and so now these so this S mu. So when we pick which k columns to remove, these correspond to fixed points now. So let's let k be 0. So we're not removing any columns. So this is counting just the total number of colored permutations. And so now when k equals 1, we're looking at this sum is now counting the number of colored permutations where I have exactly one fixed point where it gets mapped to its same color. And then for k equals 2, I'm counting all the ways where I can have two fixed points where they both get mapped to the same color. And so right, and so so what we're doing here is we have this alternating sum here. So this is just an inclusion-exclusion argument. And so that's exactly what we wanted to count over here on the right-hand side. So this is, yeah, and so probably the best thing to consider would be to convince yourself of this if you're getting lost is to plug in lambda equals the trivial partition. And then in this case, you'll quickly see that, yeah, this is just, we're just recovering the result that we talked about on the first slide. Okay, and so a similar proof goes through for alpha equal to 2, but I won't discuss that here. Okay, so yeah, I guess let's pause for a moment. Are there any questions about this proof or the main result or anything that we've talked about thus far?
So are you saying that the alpha equal 2 case is also just an inclusion exclusion, but with the details more complicated? Yeah,
exactly. So here, yeah, this instead of going over, so okay, so we didn't really talk about what colored perfect matching is. I sort of just alluded to the fact that you can also define them in a very similar but slightly more fiddly way. You can also define perfect matching derangements in sort of the same way. And now because we're dealing with a set here, so this D lambda 1 is an actual set that we can count using inclusion exclusion. We can do the same for D lambda 2. So it's actually a set of colored permutations or perfect matchings. So with other alpha, you don't really you don't have this luxury, right? So there's like for alpha equals to 3, I don't know of an actual set that I can count using the principle of inclusion exclusion here. And so that's why this alpha equals 1 and alpha equals 2 case is easy, because there's actually some concrete combinatorics that you can connect, that you can connect to.
Great, thanks.
Yeah, good question. Cool. Okay, so so this is already. So I wasn't aware of this interpretation. So it's. I mean, it's. I think it's nice because when you think of the permutation. So remember that eta lambda 1, those are the eigenvalues of the permutation derangement graph. So this says that the eigenvalues of this graph are they're colored derangements rather than just the traditional derangement. And the traditional derangement is like is lambda equal to the trivial partition, and that's also the degree of the permutation derangement graph. So yeah, I think it's a nice formula. It's just that it's how do you actually evaluate these things? And so that's for example, like if I have a partition mu and I consider all colored permutations for S mu, like what's the size of that set? Okay, so we'll see what that is momentarily, but a priori it's not obvious. So and I should mention that there's other formulas for the these eigenvalues of the derangement graphs. Like there's an alternating sum that's a ratio of determinants. It's not easy to evaluate that, and this expression likely doesn't exist for the perfect matching derangement graph. So these are difficult to evaluate. So there's also several recurrences known. Those are also equally, if not more difficult to evaluate. So really what we want is like a simpler closed form expression for eta for these eigenvalues, right? And so yeah, so we're studying these Jack derangement sums, but like the real motivation that I had, at least for studying them, was to complete this goal, that is to find like nicer expressions for these eigenvalues. And it just turns out that actually working with this parameter alpha is a more elegant way of going about doing this. Okay, so yeah, so the remainder of the talk, we're going to focus on this goal. So there's this thing that I'm calling the principal lower hook product. Okay, so here, so I think a picture here is worth 1,000 words. If you've seen some character theory, the symmetric group, this A lambda and this L lambda, this is the arm length and the leg length. So this is the lower hook length of the cell ij. So for instance, if I were to look at this cell right here, in first row, third column, there's 7 cells to my right. So I have a 7 alpha. There's 2 rows below. There's 2 rows below me. So I have a 2 here for my leg length, and then I add 1. So I have 7 alpha plus 3. So the principal lower hook product is just going to be the product of all these lower hooks on these lower hook products along the first row. And so if you're confused why we're talking about lower hook products, well, that's because there's this thing called an upper hook product, and it turns out that we won't need it for this talk. Okay, so right. So in some work with Yuval that I mentioned earlier, we actually came up with, so this appeared in the Formal Power Series in Algebraic Combinatorics 2022. We actually have some nice counts for these sets that we've talked about before. Remember S sub lambda, that's a colored permutation, like these lambda colored permutations and lambda colored perfect matchings. So for various values of alpha, we have that this product here, this principal lower hook product, counts the number of lambda colored permutation, and it counts the number of lambda colored perfect matchings. Okay, so and actually we weren't the first, I think, to come across this. So this expression, it comes up in some old work on invariant theory, actually. So if you're familiar with this thing called Cayley's omega process, so this is a differential operator that pops up in invariant theory. So if you want to apply that operator, like if you want to apply that operator to a determinant, particular type of determinant, then I think an old result of like Williamson shows that, I hope I'm getting that name right, shows that these numbers pop up when you apply this differential, like Cayley's omega process, to whenever you apply them to determinants for alpha equals 1. Okay, so so these numbers have these principal lower hook products popped up for alpha equals 1 in the invariant theory literature. So I just wanted to make a note of that. Okay, so this gives us, so going back to our formula that we had. So remember before, this was like this complicated sum of Tableau transversals of size lambda 1 minus k. So now we've got something a bit more concrete. So using some previous work, we're just plugging in this principal hook product now. So now remember that mu is going over all ways that I can remove k columns from lambda. So this is all such shapes that I get by plucking k columns of lambda out. And so I take the principal hook product of each of those and I sum them up, and that's what I get. Okay, and so for lambda equals n and alpha equals 1, this expression above, it just translates to this familiar principle of inclusion and exclusion for the number of derangements. Okay, so the problem is that this is still too difficult to work with, right? So in particular, we're going over lambda 1, choose k terms here, right? So in each of these terms, I mean, the shapes that I can get by plucking k columns out of an arbitrary shape lambda, I mean, there's lots of possibilities. So I could be looking at a lot of different types of principal lower hook products here. So it's there's still some work that needs to be done. Okay, so this is what so the fact that this is quite complicated got me into looking at properties of this principal lower hook product. And it turns out that when you study this principal lower hook product, it has a lot of properties that are reminiscent of the determinant. And so I'm going to say that it has like a Laplace-like expansion. So what do I mean by that? I mean that I can write the principal lower hook product as a weighted sum of principal lower hook products of smaller hook or of smaller shapes that are contained within my shape. So let me be a little bit more concrete about that. So lambda minus I is going to be the shape that we get by just removing the ith column of lambda. And we're going to use this shorthand throughout this work now. So remember that this was this lower hook product. So this was, so I take the cell 1j and I look at the number of cells below me, and I add that to alpha times the number of cells to the right of me plus 1. Okay, so we're calling that hj. And so we were able to show that these principal lower hook products, I can write them out as a like a cofactor expansion, sort of, where I have each of these. So each of these smaller principal lower hook products obtained by removing a particular column, I weight that by alpha, except the last one, I weight that by h sub lambda 1. So this hook length of the far right cell in the first row. Okay, so you get, so yeah, I think this is pretty cool. Nice thing about it is, so it's pretty technical. I won't get into it, but this generalizes to k minors. So if you want to think of each of these terms, each of these h1 lambda, each of these h1 lambda minus i's as being like a first minor of lambda. Yeah, so this generalizes to where I'm removing not 1, but I'm removing k. So I get a different expression. And so that this lemma is like quite technical. It's the brunt of the work in this paper. But the nice thing about it is that through these properties of principal lower hook products, in particular these minors that we're talking about, you actually get a really nice expression for Alex Anderson and Fourier's expression. So remember, Alex Anderson and Fourier showed that this thing was, so we had these shifted jack polynomials, and they showed that you could write this as a sum of over Tableau transversals where they were alpha weighted. And then we showed that that these alpha weighted tableaus, these things, we can count those by considering these principal hook products. And so now through the lemmas on the previous slide, this complicated sum here, we can write this actually as something quite concrete. So this, so remember, this HI is the lower hook length of the cell, of the I cell on the first row. And so I guess if you've been around the block, then maybe you notice, it took me forever to notice this, but like the right-hand side is essentially this kth forward difference of a particular polynomial, and this polynomial is defined as follows. So we have right, so we have this polynomial that's essentially the numerator here on the right-hand side. So where it's a polynomial in X, and there's this polynomial has degree lambda 1, and so we take the kth forward difference of this polynomial and we evaluate it at the origin. So this is okay. So this is a somewhat complicated expression if you haven't seen all these symbols before, but this kth forward difference is defined down here at the bottom. So we're essentially looking at the kth forward difference of this polynomial, and remember that so this is just one particular shifted jack polynomial, and remember that our formula for the jack for these jack derangement sums, this was an alternating sum. So we had a -1 to the k here, where k went from 0 to lambda 1. So we have like this alternating sum of these guys, and it turns out that this alternating sum of these kth forward differences, what's happening here is that we're essentially writing out what is a Newton polynomial. So these kth forward differences go hand in hand with these Newton interpolation polynomials. And this is all something that is wrapped up in the calculus of finite differences and falls under the umbrella of this thing called the umbral calculus, which is something that Rhoda and his disciples studied a lot in the last century. So I won't get into the details here, but this is sort of like the key observation is that we're staring at like this expression here, this new way of writing Alex Anderson and Fourier's result gives us just a way of explicitly writing down what the Newton polynomial is. All right, so basically, to wrap things up on this slide, it's we get some sort of polynomial interpolation here. And the polynomial interpolation, I should say that the polynomial interpolation that is happening here, it's these Newton polynomials, they're defined with respect to the following factorial basis, which we'll see on this next slide. Okay, so once we have that previous expression, we get this nice, it turns out that there's like this nice connection to the Poisson distribution, but from the previous slide, you can write down this expression. So it seems complicated, but really what's happening is like the fact that we can write down the Newton polynomial of this polynomial h1 lambda x. The fact that we can write that down, basically, yeah, it's telling us that we're staring at moments of the Poisson distribution. So right, so I should say that's only true for positive alpha. So this theorem also holds for negative alpha, but it has a nice probabilistic meaning when alpha is greater than 0. Okay, so I guess since we've got about 5 minutes left, so I'll say that from the previous, so using the fact that we're doing polynomial interpolation, we can get from the previous expression to this expression. And these these D coefficients here, these are classic numbers. These are things called the Ron-Contra numbers, which are generalizations of the derangements. In particular, this for alpha equals to 1, this counts the number of permutations that have precisely k fixed points. So when k equals 0, we get the derangement numbers. So we get these nice coefficients here that are related to like derangements and partial derangements. And so if we have alpha equals to 1 and I divide by n factorial, then I get the probability that a permutation has precisely k fixed points. Okay, so we get a nice connection to the Poisson distribution. So we get, like, what you could call generalized factorial moments when alpha is positive. Okay, so I'll give a quick sketch of the main result. So basically from that previous expression, thinking of it as moments of the Poisson distribution, using this limit here, it makes sense to write this polynomial h1 lambda x and the basis of alpha falling factorials. And so that's what, so this x lambda, so this x k, I guess underline is our notation for x times x minus 1 times x minus 2 ... times x minus k plus 1. Okay, so so this gives a basis for univariate polynomials in X. And so we write that polynomial in this basis. And what that accomplishes is that it kills off both X and this pesky scalar here. And so it turns out that the leftovers give us a polynomial in alpha. And what's that polynomial in alpha? Well, it's those Jack derangement numbers that we defined several slides ago. And so there's some non-trivial combinatorics that's involved in getting and realizing that what's left over after we take limits is this polynomial in alpha. But that's essentially the gist of the proof. And so that's so that's a sketch of the main, a very sketchy proof of the main result. But like, remember that our goal was to get nicer formulas for alpha equals 1 and 2 as well. So it turns out that we can actually do that. We can actually do quite well. So for alpha equals 1 and 2, so we'll just focus on alpha equals 1. So that's the permutation case. So notice that a lot of terms in this sum here vanish when alpha equals 1 for arbitrary shapes. So if I pick just a random shape where my rows have various sizes, if there's any overhang, then like let's say that I have an overhang on the first row, then that's going to mean that when j equals 1, this evaluates to 0. Okay, so like I take the first principal hook product, or when this is 0, I just recover the principal hook product. And when j equals 1, I'm plugging in 1 to this polynomial, and then I get this shifted, like it's like a shifted principal hook product, and 0 is going to be one of those terms, or one of those factors. Okay, and so so we got about a minute left, so I'll briefly talk about this other type of hook product that comes up in getting the simplified expression. So here's a shape lambda. I've labeled lambda with all of its hook lengths. And so all the hook lengths are as follows. You can think of these as lower hook lengths, makes no difference. So now consider what I'll call like the complement shape, which is like the negative space whenever you complete this to like a rectangle. So do the same thing for these rows here in this negative space. So we're labeling them with hook products, or sorry, with hook lengths, and we're kind of reflecting about the XY axis. And now combine those two together, and I'm calling the product of all the numbers along these rows the extended ith principal hook product. So so we're extending. So for instance, the second principal hook product, the second extended principal hook product of lambda is going to be 8 times 6 times 5 ... times 1 times 2 times 3 times 4. Okay, so in the last 30 seconds, I'll just briefly flash this in front of us. Recall in the previous slide we discussed that these we have these probabilities for the, so we have these run contra numbers, and when we normalize them by the factorial, we get the number of the probability that a particular permutation drawn from S lambda 1 has exactly J fixed points. And there's a nice formula for that. And so we get this nice formula here that's completely, so we only need to look at hook products. We don't need to do any recurrence. We don't need to do any sort of determinant calculations. That's it. So this is, I think this is as good as it gets for alpha equals 1. So I'll close, I'll just leave this slide open, and I'll let y'all read this, but I think we're officially out of time. So I want to thank everyone for your attention.